Assalamu alaikum students. We are in class 12 physics. Today we are discussing the topic torque on a current carrying loop or coil placed in magnetic field. Okay. See here is the loop. This is the loop P, Q or S. Okay. Loop means single turn of a coil. Single turn of a coil, we call it as a loop. That it carries current I. Electric current is flowing through this loop, and this system is placed in magnetic field B, right? We know when this loop is placed in the magnetic field, when the current is also flowing through the loop, torque gets developed upon the loop. Meaning, torque, should you know that it is a force which makes the body to rotate on a given axis. It makes the body to rotate on a given axis. That force we call as torque. So we have to calculate the torque. Okay, let us write down these things. See, let P QRS is a loop carrying current I placed in magnetic field B. Okay. Now we know when these conductors carrying current as remain in magnetic field, forces get developed upon it. Those forces then constitute the torque. Okay. Now first we calculate the forces on all of these arms. First this arm, this arm, this arm and this arm. Then after getting the resultant force, we can get the total torque. Okay. So now let us calculate the forces upon the arms of this loop, right? Now see here I have written force on arm SP. Let's calculate force on this arm SP. We know the relation when the current carrying conductor is placed in magnetic field. The general relation for the force which is experienced by that is given by F is equal to I. L means the length of that conductor into cross product with its applied magnetic field. Okay, this is the previous relation which you have gone through. Here we can then write, let us talk the force for this arm SP. That will be given by I means the current which is flowing through the loop. Okay, it will be everywhere the same. Current I is same everywhere in the loop. Okay, so that current L means the length. Here we are talking of this length. This is the breadth of this. If we are here, then or here, then it will be the length. But here is this sort of the length, and it is denoted by B, the breadth. So the length, okay, into magnetic field, right? Same is the case for this arm QR. Let it be denoted by force F2 is equal again current the same, and it is how much is the length of it? It is denoted by P, small b, into applied magnetic field, right? So these are the two forces which get developed upon this arm and this arm, right? But if we apply, this is an important and interesting thing to know. Now we have to apply Fleming's left hand rule to get the direction of the force. See, this is my left hand, and we know this finger, this thumb, this middle finger and this index finger. This middle finger, it denotes electric current. Okay, this denotes magnetic field, and this denotes the force experienced by this conductor. Let us apply this here. See here, this is the current. Current is coming to in this direction. This is the current. See, this is the current. This is the magnetic field direction. Then the direction of force is upwards. Okay, so this force will act in upward direction. F1. So the force upon this arm will act upon in upwards, like by this application, this Fleming's left hand rule. Now let's apply this rule upon this arm. See here, the current was coming from S to P. Now here current comes back and it goes from Q to R. Now apply again the same rule. We will see this force like this. Okay, see, this is the this denotes the electric current. This denotes magnetic field. Okay, magnetic field goes from here to there, and this is what? This is the direction of electric current. Then again the force comes here in downward direction. So I can make it like this. This is magnetic field. This is the breadth of this coil. this is the next force. F2. Now it is clear here that this force it acted upwards and this force acted downwards, right? But and the other values were same, current is same in both the cases, length is same and applied magnetic field is same. So the two relations are of equal value. They are of equal value, but the forces which we got here, they are in opposite directions because this is upwards and this is downwards, okay? But line of action is same. So these two forces are in equal magnitude but opposite direction with the same line of action which I have written over here. So these two forces will cancel each other. I have written here. So the total resultant of the two forces will be 0 because the two forces are acting in opposite directions with the same magnitude. So the total resultant force upon this arm and this arm comes to be 0. Now let us take these two arms, this arm, meaning let us take the length of the coil, okay? Now see, this is the force on arm PQ, okay? Again the relation is same. This F is called I, length into bracket. Here the length is again denoted itself by length, okay? In the previous relation, length was denoted by B, the breadth, okay? But the other things are the same. ILB, it comes to B because here I have used, I have solved it in the next to the next step. That A cross B means AB sine theta, LB sine theta. But the theta here is 90 degree, okay? Theta is the angle between length and this applied B, capital B, the magnetic field. This is the length and this is the magnetic field. The angle here is then the 90 degree. Okay, the angle is here 90 degree. So sine 90 means 1. This comes to B. I is called LB, right? But the interesting thing here to apply is again the Fleming's left hand rule. See, now let me take again this Fleming's left hand rule. Center finger denotes current. This is the magnetic field and this is the force for this arm. See, current here comes downwards. This is the direction of current, it comes downwards. Okay, this is the direction of magnetic field to this way, and the force is here out of the board, out of your paper. Okay, so the force upon this arm will act outwards, perpendicular to this board or paper, which I have written here outwards, right? Perpendicular to plane of the coil, right? This was for this arm. The same, let us apply for this arm, R and S. But here one thing is the difference, that the direction relation will be same because current is same, length is same, and applied magnetic field is again the same. So we will get the same relation, but the direction of force will have to be seen by this Fleming's rule. Here in this case the current was coming down. Now here the current is coming upwards because this is the motion of current is here the anti-clock. Here it comes here, then comes down, then goes here, then comes up. Okay, now apply this. This is the electric current. This time current is moving upwards like this. Current is upwards and direction of magnetic field is to that wards. So the force will act inwards to the board, which I have written here. This by Fleming's left hand rule, this force is perpendicular to plane of coil, directed inwards like this. Okay, this force was outwards and this force is inwards. Okay, so when the two forces act upon the body in the opposite direction but with this different line of action. See, this line of action means here it is in this line, okay, acting inwards, and in this this arm the force is acting like this outwards. So two lines of action. One line of action is this at this edge and next is at this edge. So what will happen? It will rotate, meaning this force will take it to inwards and this force will take it to this end outwards, meaning it will start rotation like this. So the couple is created here, which creates the torque, meaning the rotational motion to it, right? This thing I have written here. These forces F3 and F4 are equal and opposite but have different lines of action. which I make you to understand. This is here, one force is here at this axis, and next is at this axis, meaning at this line, right? But in the previous case, the forces were at the same line, here and here, meaning upwards and downwards in the same line. Here forces have two different lines, so they have different lines of action, so will form a couple, and so the torque about the dotted axis gets created here. This is the dotted axis, so torque will be experienced in the coil about this axis. See, I can demonstrate you like this. See this, if this is one loop, okay, like these are my fingers which represent the magnetic field lines, okay, like this. See here I have shown, this is the length of the coil, okay, this is length of the coil, and this is breadth of the coil, okay. This length makes angle 90 degree with it, which I told you that 90 degree case, and the sign 90 came to be 1, okay. So this is the how much will be the rotation of this coil, okay, this loop. The 90 degree angle will remain same because it's the angle between length of the coil and direction of magnetic field. First point. Now second force, the talk of the forces. See the forces, force F1 and F2. F1 force that was acting upwards like this, and in the same line the F2 that was acting to this arm in the downwards, meaning this force attracted it to downwards and this force to upwards, meaning, but these two forces were equal and opposite, so they cancel out each other. So the resultant of these two forces, F1 and F2, it came to be 0. But if we talk of these two forces upon the arm, this arm and this, meaning this arm and this arm, right? L, length. Here we understood that the force F3, it worked upon his outwards, meaning it acted upon this arm outwards, like this. And upon this arm, the force acted inwards. So here the force is acting to this way, and here the force is acting to inwards, so it will, and these two forces have two lines of action. This is one line, and here this is the next line, so they will make the body, this loop, to rotate. This force will bring it in forward, and this force will bring it to backwards, so it will rotate like this. So this is the rotating this force upon it. Now this mathematical relation for this torque is called magnitude of either forces. So two forces, the two forces which got developed, which gave the result for the torque, meaning this F3 and F4, magnitude of either two forces into perpendicular distance between the two forces. This thing you would have gone in the 11th class also, the perpendicular distance between the forces. Let's calculate it over here. Magnitude of either forces is given in equation number first or second, only the magnitude, no direction. So that equation number first or second is ILB, the force, this F3 force or F4 force, which constituted the torque. So magnitude of either force into perpendicular distance between the two forces. See, this is the thing. This is one force and this is the next force. This is its line. This is the line of action of this force and this is the line of action of this force. The perpendicular distance is this, which is the perpendicular between the two forces. This force perpendicular and the perpendicular upon this. Okay, so this is the perpendicular distance between these two forces. Perpendicular this here, and here again is a perpendicular. So this is the perpendicular distance between these two forces, meaning between F3 and F4. So what is it? It is NS. Okay, now let's calculate this NS from this triangle, and we know to calculate this NS, let us take this triangle NPS, okay, PNS, and calculate cos theta by this relation based by hypotenuse, and we got this NS is equal to B cos theta. Well, theta is angle between, this is important to know, theta is angle between magnetic field and plane of the coil. This is the plane of the coil, okay, and this is direction of magnetic field. If the plane goes to this, a little, let it gets rotated. This is the magnetic field direction. Then how much will be the angle between plane of this coil and this applied magnetic field? It is the angle theta, okay. So use this NS for this value, ns, it is b cos theta over here. So we get torque tau is equal to I L B, and value of bs, it comes to be b cos theta. But see, this is L, small l, meaning the length, and small b the breadth. Length into breadth of the coil is the area, of the coil. So replace this LB by area A, we got torque tau is equal to I L into small b, meaning the area, it is capital A, and b cos theta. So this is the general relation for the torque for the single loop of the rectangular coil. Okay, for now this was for one turn, here it is 1. If we have 2 turns, we have to multiply it by 2. If we have a coil which is having like n number of turns, then here we have to multiply the coefficient n. So we get, for coil with n number of turns, the torque is given by n I A B cos theta. Okay, see, you may see in some books or in some notes, on some notes here, the sin theta. Okay, this is the confusing thing to take into your mind, that we are here having the angle theta. It is the angle between plane of the coil and direction of the magnetic field. Now let us take another angle, which will be the angle between normal of the coil and magnetic field. Okay, see, I have taken here only PS arm. This is only the PS arm here, and I did this mathematical and these triangles angles. I was here discussing only the arm PS, and I got this relation, right? I'm not talking that I got the relation, this relation only for this arm. No, it is the total torque upon total loop, okay, and total coil. But to calculate some of the factors or some of the things, I took only this arm PS for the factor. Okay, see, this is the plane of the coil. Okay, let me draw the normal to it. Okay, n is the normal, and alpha is the angle between normal and magnetic field. Here I have written alpha is angle between normal of the coil and magnetic field. Okay, then since normal is 90 degrees, so this to this up to this, it is 90, meaning theta plus alpha, it is 90 degree, and theta comes to be this. Use this value of theta in the previous equation, as equation number 5 and 6. Okay, we will get cos of, here comes to be 90 minus alpha, because theta came to be 90 minus alpha, and we know that cos of 90 minus angle, it gets us converted into sine the angle. Angle is here, it, so cos 90 minus alpha, it comes to be sine alpha. Same for the next equation, that equation number 6, which is for, this is for loop of single loop, this is for whole of the coil with n number of turns, it will get converted into this relation. Okay, let me proceed forward. NIA, number of turns, current, and area of the coil, it is equal to M, capital M, meaning the magnetic dipole moment of the coil loop, magnetic dipole moment, which you would have gone in the previous topic. So this gets converted into M. Okay, so we will get MB sin theta. Here it is M, and then B, MB sin theta, and we know AB sin theta comes to be A cross B, because this is a vector product. So in vector product, A cross B is equal to AB sin theta. So torque for whole coil can be written also as M cross B, right? So this was a long problem to solve, but easy to understand. I hope you would have gone through it, you would have understood it, but if you won't get it, repeat and repeat this lecture, and inshallah you will get through.